Welcome to Shanti-Peace for Mathematics. In this video, we are discussing about the uniform convergence of the Fourier series. In my previous video, I already defined what do you mean by Fourier series. The Fourier series means this trigonometric series is called the Fourier series if this A0 is nothing but the 1 upon pi minus pi to pi f of x dx. An will be 1 upon pi minus pi to pi fx into cos nx dx, and Bn is 1 upon pi minus pi to pi fx sin nx dx. Here also we are going to discuss this proof of this theorem. This is the theorem which tells you that this series is uniformly converged to this f of x. Then we can prove that this series is nothing but the Fourier series. That means this A0 is this, An is this, and Bn is this. Here there is one more word is used. We have used that this called the uniformly convergent series. So when we can say a series is convergent if its partial sum is convergent, but it is about the numbers. Here it is the function is there. So in the function there will be two types of convergence is there. The one is the pointwise convergence. Another one is uniform convergence. The pointwise convergence means the series is converging point by point, and every uniform convergence is pointwise convergence. But the converse is not. I am giving you a definition of what you mean by uniform convergence of a series. So summation of ft of x is a series of a functions. If I want to say that the series is convergent if its partial sum Sn of x is summation k running from 1 to n, ft of x is uniformly convergent to a function f of x, then we can say that this series is uniformly. Now what do you mean by uniformly convergence of a sequence? Because Sn is a sequence now. Uniformly convergent sequence is defined like this. Let's say this fn of x is a sequence of functions. If I want to say this is uniformly convergent for given epsilon greater than 0, that exists n0 belongs to n, depend only on epsilon, not depends on x, such that mode of fn of x minus fx is greater than epsilon for every n greater than or equal to n0. And this is true for every x in the domain of the function. Let's say domain of the function is E. Then we can say that fn is converged to f uniformly. So this is the definition of uniform convergence. You are going to discuss about the uniform convergence in the next semester. But till now you just see this definition about the uniform convergence. Now what is the advantage of this uniform convergence? The advantage of this uniform convergence is you can interchange the integration and the summation sign. So in general you cannot write down this is the things. N of x is there, then you cannot write down in general this thing. You cannot interchange this summation and the integration. Under the uniform convergence, you can do that. So that's why this uniform convergence is required to obtain this result. So we are assuming this series is uniformly converged to the function f, and then we have to prove that it is nothing but the Fourier series of the function. Let us try to prove now that theorem. Given that this series a0 by 2 plus summation n running from 1 to infinity an cos nx plus bn sin nx is equal to f of x, because it's given that it is uniformly convergent. Now I'm integrating both sides with respect to x in the interval minus pi to pi. So what will we get? We get this is interval minus pi to pi a0 by 2 dx plus summation n running from 1 to infinity an Now here I can interchange the summation and the integration sign because of uniform convergence that are discussed in the previous case. So that's why this integration I can take it inside. If it is not uniform convergence, we cannot do in general that thing. So that is, we can write down in this fashion, is equal to integration minus pi to pi f of x dx we have. Now this quantity will become 0, that you can check, because the integration of cos is sine nx upon n. We apply the limit minus pi to pi, sine n pi is 0, sine minus n pi is also 0. So for that is also 0 answer. Here is also a 0 answer for any n, which is from 1 to infinity. So only the quantity is left is there. So I can rewrite this whole expression as minus pi to pi f of x dx is equal to a0 by 2 into x. Integration is from minus pi to pi. That's why this would be a0 by 2 into 2 pi, and this 2 will cancel out. So we'll have a0 will be 1 upon pi minus pi to pi f of x dx. Now next f of x is a0 by 2 plus summation n running from 1 to infinity an cos nx plus bn sin nx. And if you want to get this now an, then I want to multiply this equation by cos mx. Now m is a fixed integer. I am fixing m, which belongs to n. So I am fixed this integer m, and I am multiplying this whole expression by cos mx, and then I am integrating in the interval minus pi to pi. That's why it is integration minus pi to pi fx cos mx dx equal to a0 by 2 is a constant quantity, so I can take outside in the interval minus pi to pi cos mx dx plus summation n running from 1 to infinity. Here also I am using the property of the uniform convergence, that you can integrate, means you can interchange the summation and the integration sign. So that's why it is minus pi to pi. En is a constant quantity, so it is cos nx cos mx dx plus summation n running from 1 to infinity bn minus pi to pi sin nx cos mx dx. Now just observe what is this quantity, that is minus pi to pi cos nx cos mx dx. This is 0 if m is not equal to n, and this is equal to pi if m equal to n. So if I use this one here in this integral, only nth term is left, because this is summation 1 to infinity. When n is equal to m, then the quantity left, which is pi. Otherwise, all the quantities, all the summation inside the summation is 0. And about this one, minus pi to pi sin nx cos mx dx will be 0 for any m. So this quantity will become 0 for any m. But here this is pi if m equal to n. This is already 0, which we have proved. So finally what is left? The left quantity is am into pi, which is this side is left. Now this side you will have this integration minus pi to pi f of x cos mx dx. So which will implies am will be 1 upon pi minus pi to pi f of x cos mx dx. Lastly, in the similar manner, as we have multiplied here with cos mx, if you want now bn, then you have to multiply with the sin mx with m fixed. So let us write down what you will get if I multiply sin nmx and integrate both sides with respect to minus pi to pi, with respect to x in the interval minus pi to pi. So finally, we have integration minus pi to pi fx sine mx dx is equal to, the first one is a0 by 2, the integration minus pi to pi sine mx dx plus summation n running from 1 to infinity en integration minus pi to pi cos nx sine mx dx is there, plus summation n running from 1 to infinity dn minus pi to pi sine nx sine mx dx. Again, this quantity will become 0, this is also 0 for any NMN. So this quantity, these two summation quantities are 0. Now for this also we have a similar result as we have did with the cos, that is sine nx into sine mx is equal to 0 if n equal to m, and it is pi if n is not equal to m. So this is finally we have it as Bm into pi, because for m equal to n, I have written wrongly. If it is not equal to, then it is 0, and if it is equal to, then it is pi. So that's why it is Bm pi, because this is not equal to, then it is 0. And so finally we have Bm equal to 1 upon pi minus pi to pi f of x sine mx dx, and this is true for any m. So that's why we can say that this, if this is uniformly convergent, then this series is the Fourier series of the function. Here I have written 2 pi, but it has to be pi in each and every coefficient we have. Now to establish the Fourier series, I require certain things to discuss right now. The first one is f is an odd function. When we can say the function is odd, implies that f of minus x is minus of f of x. For every x, if it is true in the interval minus a to a, then we can say that f is an odd function. And you just know that if it is function from minus a to a, f of x dx, we can write down this is as 0. If f is an even function, then f of minus x is f of x for every x in that interval minus a to a. That is called the even function, and the integration for even function, that we can write down 2 times 0 to a f of x dx. Now what is the advantage of this even function and odd function? If your function f is an even function, let's say, then the Fourier series will be converted into f of x equal to a0 by 2 plus summation n running from 1 to infinity an cos nx. The bn term will not be there, because you just see that the formula for bn, you have this formula for bn is this, and your function f is an even function, and this is an odd function, because you know that the sine of minus x is minus sine x, so that's why it is an odd function. And you know that the even function into odd function is again an odd function, so that's why, and the limit is from minus pi to pi, so that's why this will become 0. And in other words, what is your a0, which is, we know the formula is minus pi to pi f of x dx, and your function f is an even function, so that's why it is 2 times, we can write 0 to pi f of x dx. And an will have, it is again the same thing, minus pi to pi f of x cos nx dx. Now you just see that the cos is an even function, fx is also an even function, even into even function is also an even function, so that's why this is 2 times 0 to pi f of x dx. So the advantages of if your function f is an even function in the interval minus pi to pi, then you can having only a cosine series in that. And if you have an odd function, then your f of x will be summation n running from 1 to infinity bn sine nx, where bn will be 2 upon pi 0 to pi fx into sine x. That we can see. That's it for this video. See you in next video. Bye bye.